We tend to think of the cosmos as quiet, a vast, empty vacuum where stars shine undisturbed and planets orbit in silence. And for the most part, that's true. Space is mostly space, empty, cold, and still. But when things move, and everything in the universe is always moving, they sometimes cross paths. And when they do, the silence ends. Collisions are among the most violent and creative forces in the universe. They can obliterate planets, trigger star formation, reshape orbits, ignite fusion, and end entire epochs of life. But they also build. They sculpt moons, seed atmospheres, stir chemistry, and create entirely new structures. In space, destruction and creation are often the same event, separated only by time and perspective. Our own planet, Earth, stable and blue and familiar, is the result of catastrophe. Every continent, every ocean, every living thing you've ever seen exists because, long ago, things slammed into each other. It started at the very beginning. In the early solar system, there were no neat orbits or planetary harmony. There was only chaos, a swirling disk of gas and dust, where collisions were constant. Small bodies merged to form bigger ones. Bigger ones shattered into fragments. And occasionally, something huge would hit something else at just the right angle to change everything. This period is known as the Late Heavy Bombardment, a violent phase about 4 billion years ago, during which asteroids and comets pummeled the inner planets. Earth, Mercury, Mars, and especially the Moon still bear the scars. On the Moon, there's no atmosphere or weather to erode those impacts, so the craters remain like a fossil record of the solar system's turbulent youth. But not all collisions were random. Some were orchestrated by gravity, by the giant planets shifting positions, disturbing the orbits of icy bodies and flinging them inward. Jupiter and Saturn, in particular, may have caused a gravitational resonance that destabilized entire populations of asteroids, sending them crashing toward the inner solar system like a shotgun blast of rock and ice. And these impacts weren't just destructive. Some of them may have delivered the ingredients for life. Comets, rich in water, organic molecules, and carbon-based compounds, could have seeded the early Earth with the chemical precursors of biology. In that view, life didn't arise despite collisions. It arose because of them. Of course, not all impacts are ancient history. Even now, Earth crosses paths with cosmic debris on a regular basis. Most of it burns up in the atmosphere as harmless shooting stars. Occasionally, a larger object makes it through, like the 20-meter asteroid that exploded over Chelyabinsk, Russia, in 2013, injuring over 1,000 people from its shockwave. And even larger impacts? They're rare, but not impossible. About once every few million years, Earth is struck by something big enough to cause global consequences. We'll explore one of those, the asteroid that ended the age of dinosaurs, in the next chapter. But for now, consider the scale. A 10-kilometer asteroid doesn't sound like much compared to Earth's size. But traveling at tens of kilometers per second, it delivers energy equivalent to millions of nuclear bombs. The result isn't just a crater. It's firestorms, tsunamis, months of darkness, and mass extinction. And the worst part? There's no cosmic defense system, no natural shield, just probability and time. But impacts don't only threaten, they also transform. In fact, many planetary features we now study as scientific puzzles began with violent collisions, impact basins, tilted axes, even planetary spins. Mercury's thin crust? Possibly the result of a colossal collision that stripped away its mantle. Uranus's sideways tilt? Likely caused by a glancing blow from a planet-sized object. And our own moon? As we'll see, born from a collision so vast it fused two worlds into one. So if the universe seems peaceful, it's because we're living in the intermission between cataclysms. The soundtrack of planetary history is not constant hum. It's boom, silence, evolution. And somewhere, even now, another boom is on the way. It's easy to forget that the moon is a world. We see it so often, glowing silently above us, that it begins to feel more like a backdrop than a body. But the moon is massive, ancient, and, perhaps most astonishing of all, it wasn't always there. Its presence is so familiar, so tied to tides and calendars and mythology, that we rarely ask the question, where did it come from? The answer, it turns out, is one of the most spectacular collisions in planetary history. Roughly 4.5 billion years ago, not long after Earth itself had coalesced, a planet-sized object slammed into it. This wasn't a glancing blow. It was a catastrophic impact between two massive bodies, Earth and a hypothetical planet scientists call Theia. Theia was likely about the size of Mars. Its orbit had become unstable, perhaps nudged by the gravity of other forming planets. And eventually, its path crossed Earth's at precisely the wrong moment. The impact was beyond anything we can properly imagine. It didn't leave a crater. It melted the crust. It vaporized rock. It sent plumes of molten debris into orbit. For hours or days, Earth may have been surrounded by a glowing halo of fire, a disk of searing material, torn from both worlds. And from that chaos, the moon was born. The molten ring of debris slowly cooled and coalesced. Gravity pulled clumps together. Smaller pieces merged into larger ones. Eventually, a single massive object formed, orbiting the still molten Earth like a glowing ember. That object would become the moon. This idea, the giant impact hypothesis, is the leading theory for the moon's origin, and it explains several things that other models could not. For one, the moon is large, unusually large for a planet-moon system. It's about 1/4 the diameter of Earth, and its gravitational influence has shaped our planet's tides, axial tilt, and even its long-term stability. For another, the moon is compositionally similar to Earth's outer layers, particularly the mantle, but lacks the heavy metallic core that Earth possesses. That makes sense if the moon formed from debris blasted off Earth's surface, rather than being a captured object or a sibling that co-formed in place. But perhaps most intriguingly, the moon helped shape Earth itself. After the impact, Earth's rotation would have been much faster, possibly as short as 5 hours per day. The moon's gravitational pull has been gradually slowing that spin ever since, leading to the 24-hour days we now experience. More than that, the moon has stabilized Earth's axial tilt, preventing it from swinging chaotically over geological timescales. That stability has likely played a key role in Earth's climate and in the emergence and persistence of life. Without the moon, Earth might tilt wildly, like Mars does, shifting from pole to pole over millions of years. Such changes would wreak havoc on ecosystems, ice ages, and global weather patterns. The moon's constant tug keeps Earth's spin in check, like a hand on the shoulder of a restless child. And it does more than that. The moon creates tides, pulling the oceans gently back and forth. In Earth's early days, when the moon was closer, those tides would have been stronger, vast surges of water sloshing over coastlines, mixing chemicals, stirring the shallow seas. Many scientists believe these primordial tides may have played a key role in life's origin, concentrating organic compounds in tidal pools and driving the chemical cycles that eventually led to living cells. So in a very real sense, we may owe our existence to a planetary collision. Without that impact, there might be no moon. Without the moon, no tides, no axial stability, perhaps no long-term habitability. It's a sobering thought. Something had to smash into Earth at just the right angle, with just the right energy, at just the right time, and instead of destroying the planet, it transformed it. And even today, the moon is not static. It's slowly drifting away, about 3.8 centimeters per year, as tidal forces continue to transfer energy. In a few billion years, total solar eclipses will no longer be possible, because the moon will appear too small to cover the sun. The dance that began in fire is still playing out in silence. We often speak of collisions as endings, as apocalyptic. But the birth of the moon reminds us that some collisions create more than they destroy. They give rise to balance, to rhythms, to beauty, and sometimes to life. 66 million years ago, Earth was in bloom. The planet was warm. Lush forests covered much of the land. Flowering plants had taken hold. Giant reptiles ruled the continents, oceans, and skies, from the towering Tyrannosaurus rex to the agile velociraptor to the massive mosasaur gliding beneath prehistoric waves. It was, by all appearances, a stable world. And then, in the span of a single day, it changed forever. We now know, with overwhelming evidence, that a massive asteroid slammed into Earth near what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, a scar over 150 kilometers wide and more than 20 kilometers deep. The object itself was probably between 10 and 15 kilometers in diameter, traveling at over 20 kilometers per second. The energy released by the collision was greater than 1 billion nuclear bombs. Within seconds, everything near the impact was vaporized. A shockwave flattened forests for hundreds of kilometers. Molten rock was hurled into the upper atmosphere. Earth's crust quaked, oceans surged, and wildfires ignited across entire continents. But the global consequences were only beginning. As debris spread through the atmosphere, it blocked sunlight. Temperatures plummeted. Photosynthesis faltered. Food chains collapsed, first in the oceans, where plankton died off, then on land, where herbivores starved and carnivores followed. It was an extinction-level event, and not just for the dinosaurs. Roughly 75% of all species on Earth vanished. Pterosaurs, ammonites, giant marine reptiles, gone. The world that emerged afterward was quieter, colder, and emptier. And yet, from that darkness, new life would rise. Mammals, once small, nocturnal survivors in a dinosaur-dominated world, began to diversify. They spread into the niches left behind by the extinction. They grew larger, more complex. They evolved into primates, and eventually into us. In a strange twist of fate, humanity owes its existence to catastrophe. If the asteroid had missed, dinosaurs might still dominate the planet. Intelligent life, if it evolved at all, might look entirely different or not appear at all. But how do we know all this? How can we be so sure? For decades, the cause of the Cretaceous-Paleogene extinction, often abbreviated as the KPG event, was debated. Some scientists blamed volcanic eruptions, particularly in the Deccan Traps of India. Others pointed to climate change or gradual ecological collapse. But in 1980, a team led by physicist Luis Alvarez and his son, geologist Walter Alvarez, discovered a thin layer of iridium-rich clay in sediment layers around the world, precisely at the KPG boundary. Iridium is rare on Earth's surface but common in asteroids. It was a cosmic fingerprint. That same layer also contained shocked quartz, microscopic crystals deformed by sudden, extreme pressure, and spherules. Tiny glass beads formed when molten rock is ejected and cools in the air. Later, in the 1990s, scientists located the Chicxulub crater beneath the Gulf of Mexico, buried under layers of sediment. The dimensions and age matched perfectly. The smoking gun had been found, and we're still studying it. In 2016, an international team drilled into the crater's peak ring, a circular ridge formed by the rebound of the Earth's crust immediately after impact. The cores they recovered contained evidence of ultra-high temperatures, massive pressures, and rapid recovery of microbial life in the aftermath. Because life did return, even in the midst of destruction, Earth held on. Within years, ecosystems began to re-establish. Within millennia, new species emerged. And within tens of millions of years, the planet was transformed. The Chicxulub impact is the most famous extinction event in history, but it's not the only one. Earth has experienced at least 5 major mass extinctions, each reshaping life in radical ways. Some were caused by volcanoes, some by climate, some by processes we still don't fully understand. But only one was caused clearly, directly, and violently by something falling from the sky. And it serves as both a warning and a mirror. A warning, because we know it could happen again. There are still countless asteroids and comets in the solar system, many of them large enough to cause regional or global devastation. Some pass uncomfortably close to Earth. Some are discovered only after they've already passed. But also a mirror, because that moment, 66 million years ago, reminds us how fragile life is, how thin the atmosphere really is, how quickly things can change. The dinosaurs didn't have telescopes. They didn't have space agencies or asteroid tracking systems. We do. And with that knowledge comes responsibility to understand the past, to monitor the sky, and perhaps one day, to prevent the next great collision. Because the last one changed everything, and the next one might too. When we think of impact scars, we tend to picture the battered surface of the moon or the pitted face of Mars. Craters, after all, are the calling cards of ancient violence, preserved in silence, frozen in time. But what about Jupiter? A gas giant with no solid surface, Jupiter shows no craters, at least not in the traditional sense. Its thick atmosphere swirls with storms and bands of color, constantly shifting. Any impact that strikes its clouds disappears quickly beneath the layers, swallowed by motion. And yet, Jupiter is a target, a massive, gravitational magnet in the outer solar system, pulling in comets, asteroids, and even rogue moons with silent efficiency. It's the biggest object in the solar system besides the Sun. And its gravitational influence is so profound that it doesn't just attract nearby objects, it controls the orbits of thousands of smaller bodies. Some, like the Trojan asteroids, are shepherded safely around its orbit. Others are not so lucky. In 1994, the world watched in real time as Jupiter reminded us just how violent space can be. That summer, the comet Shoemaker, Levy 9, a loosely bound chain of icy fragments, smashed into Jupiter's atmosphere in a sequence of staggering collisions. One after another, 21 separate chunks plunged into the planet, releasing energy equivalent to millions of hydrogen bombs. Telescopes around the world and in orbit caught it all. For days, observers watched as dark bruises spread across Jupiter's cloud tops, each larger than Earth itself. These weren't metaphorical wounds. They were real, tangible, undeniable evidence that massive impacts still occur in our own cosmic neighborhood. And the scars lingered. For weeks, the dark blotches remained visible through amateur telescopes, a series of planetary tattoos etched by violence. But this wasn't Jupiter's first impact, not even close. Shoemaker, Levy 9, was merely the first one we saw. Scientists believe Jupiter may be struck thousands of times per year by small meteoroids, many of which burn up high in its atmosphere and leave no trace. Larger collisions are rarer, but still surprisingly frequent. In 2009, amateur astronomers spotted another impact flash, a bright white flare against Jupiter's clouds. It was followed by more in 2010, 2012, 2016, and beyond. These observations have turned Jupiter into an accidental observatory, a place where impacts reveal themselves in ways that Earth's atmosphere often hides. But the significance of these collisions goes far beyond fireworks. Jupiter's ability to attract and absorb impactors has made it a kind of cosmic shield for the inner planets. Its gravity redirects comets and asteroids that might otherwise wander into Earth-crossing orbits. In doing so, it likely reduced the number of catastrophic impacts on our planet over billions of years. Some simulations suggest that without Jupiter, Earth might have suffered 10 to 100 times more frequent collisions with large objects. In this view, Jupiter is more than a planet. It's a guardian. But there's a flip side. Jupiter doesn't only block impacts, it can also cause them. Its gravitational pull disturbs the orbits of comets in the Oort cloud and asteroids in the main belt, sometimes flinging them inward. In fact, some of Earth's most famous impactors, including possibly the Chicxulub asteroid, may have been influenced or even delivered by Jupiter's vast reach. So which is it? Protector or threat? The answer, of course, is both. Jupiter is a gravitational gatekeeper. Unlike any gatekeeper, it controls the flow. Not always for good, not always for harm, but always with influence. It's also worth noting that Jupiter may have its own impact scars, not in craters, but in its internal structure. Recent models suggest that during its formation, Jupiter may have collided with one or more planetary embryos, massive rocky cores that plunged into the young gas giant before it fully formed. These collisions could explain some of Jupiter's unusual traits, including its diffuse core and chemical composition. In other words, Jupiter, like Earth, may carry memories of ancient collisions, written not on its face, but in its bones. And even its moons bear the marks. Look at Callisto, Jupiter's second largest moon. Its surface is heavily cratered, more so than almost any object in the solar system. Some features, like the massive Valhalla impact basin, stretch for hundreds of kilometers. Callisto, frozen and quiet, records a history of bombardment that Jupiter itself hides beneath its clouds. Other moons, like Ganymede and Europa, show signs of impacts overlaid by tectonic activity and icy resurfacing. They too are shaped, in part, by what falls from above. So when we study collisions, we can't ignore the giant in the middle. Jupiter doesn't just endure impacts. It invites them. It shapes the orbits of worlds. It carries the gravitational memory of the early solar system. It's been struck again and again, and each time it swallows the fire and continues to spin. A gas giant with no surface scars, but a history soaked in impact. They arrive without warning, pale smears of light across the sky, dragging long, ethereal tails behind them. For most of human history, comets were seen as omens, ghostly messengers from the outer dark. Their appearance often coincided with wars, plagues, or upheaval, and ancient civilizations treated them with awe or dread. But today, we know they are not omens. They are time capsules. Each comet is a frozen relic of the early solar system, a ball of ice, dust, rock, and organic molecules preserved in deep space for billions of years. They orbit the sun in vast ellipses, some returning regularly, others arriving just once before vanishing forever. And when they collide with planets, they don't just destroy. Sometimes they deliver. It's easy to focus on the destructive power of impacts, and rightly so. Comets can be fast, massive, and catastrophic. A large enough impact can vaporize oceans, change climates, and reset the course of evolution. But comets also carry something else, the building blocks of life. Let's go back 4 billion years to a young Earth just beginning to cool. Volcanoes raged, seas boiled, and the planet was constantly bombarded by asteroids and comets. This period, known as the Late Heavy Bombardment, was chaotic, violent, and paradoxically essential, because Earth, at its formation, was likely dry. The region near the Sun was too hot for water ice to survive during the early stages of planetary formation. Yet today, our planet is covered in oceans. Where did all that water come from? One leading theory is that it was brought here piece by piece by icy bodies from the outer solar system, particularly comets. Over millions of years, countless impacts may have delivered vast quantities of water, slowly pooling into lakes, seas, and eventually oceans. Not all scientists agree. Some argue that asteroids delivered most of the water based on isotopic ratios, but comets almost certainly played a role. And they brought more than just H2O. Spectroscopic studies of comets, both from Earth and from missions like ESA's Rosetta, which orbited and landed on Comet 67P/Churyumov, Gerasimenko, have revealed a stunning array of organic molecules. Amino acids, sugars, alcohols, the chemical precursors to life, have been found frozen in cometary ices. This changes the narrative. Life on Earth may not have started entirely from scratch. It may have begun with a cosmic delivery, molecules from deep space, packaged in ice, hurled toward the surface in waves of bombardment. The idea is known as panspermia, though that term often refers to the delivery of life itself. More conservatively, the theory suggests that prebiotic chemistry was seeded by impacts, that comets helped kickstart the chemical evolution that eventually led to biology. But of course, comets are not careful couriers. They don't land gently. They strike hard. The same impact that delivers organics may also vaporize rock and boil oceans. It's a paradox, destruction and delivery in one package. And yet, we know life is resilient. Laboratory simulations have shown that some organic molecules can survive the heat and pressure of impact, especially if shielded within larger fragments of ice or rock. And once in Earth's early oceans, those molecules could participate in the slow, messy process of molecular evolution, building complexity, forming membranes, replicating structures, and eventually becoming life. So comets may have helped shape not just Earth's geology, but its biology, and they still pose a threat and a promise. Most comets originate from two distant reservoirs: the Kuiper Belt, a region beyond Neptune filled with icy remnants, and the Oort cloud, a spherical shell of trillions of icy bodies surrounding the solar system like a halo. These comets are usually stable, but occasionally a gravitational nudge from a passing star or even the tidal forces of the Milky Way sends one tumbling inward. Most pass harmlessly. A few collide. In 1908, a small comet or fragment likely exploded over Tunguska, Russia, flattening 2,000 square kilometers of forest. No crater was left, but the airburst was equivalent to a large nuclear explosion. In 1994, we watched as Shoemaker, Levy 9 slammed into Jupiter. And in the distant past, comets may have struck Earth with consequences both creative and catastrophic. Looking outward, we now ask, what about other planets? If comets delivered organics to Earth, did they do the same on Mars, or Europa, or Titan? Might subsurface oceans elsewhere have been seeded by the same materials? And what of exoplanetary systems? Many of the comets and asteroid belts we see in other star systems, through indirect detection or infrared excess, suggest similar bombardments. Life, if it exists elsewhere, may also owe its origin to ice, dust, and chance. In that sense, comets are universal agents, spreading material across space, linking chemistry across worlds. They're not just messengers from the past. They may be authors of the future. And while we still study them, in orbit, in samples, in tales that stretch for millions of kilometers, we're reminded of a truth both terrifying and profound. That some of the most important collisions in Earth's history weren't acts of war, but acts of seeding. We like to think of Earth as a settled planet. After all, we've mapped the continents, cataloged the stars, and peered into the deepest parts of the ocean. But space doesn't recognize our sense of stability. Beyond our atmosphere, the solar system is still very much alive, full of motion, gravity, and wandering stones. And every so often, one of those stones finds its way to us. The next great collision isn't a question of if, it's a question of when. In 2004, astronomers discovered an asteroid that sent a ripple of unease through the scientific community. Named Apophis, it was roughly 370 meters wide, large enough to flatten a city. Early calculations suggested a nearly 3% chance that it could strike Earth on April 13th, 2029. It was, for a moment, the most dangerous object we'd ever found. Over the years, as observations improved, the risk was downgraded. Today, we know Apophis will not hit us. Not in 2029, not in 2036. But it will pass incredibly close. On that Friday the 13th, it will come within 31,000 kilometers of Earth, closer than many satellites. Visible to the naked eye as a fast-moving, it will be a spectacle, a reminder of how narrow the margins really are. And it won't be the last. NASA's Sentry system, along with ESA's similar tracking programs, monitors thousands of near-Earth objects, NEOs, asteroids and comets whose orbits bring them within $1.30 of the Sun and potentially within striking distance of Earth. Most are small, some are not. The asteroid Bennu, roughly 500 meters wide, is another object of concern. Visited by NASA's OSIRIS-RX mission, Bennu gave us both a pristine sample of early solar material and a very real sense of vulnerability. Calculations suggest a small chance of impact between the years 2175 and 2199, less than 1 in 3,000. Low, but not zero. It's not just size that matters. Velocity plays a key role. A relatively small object, say 100 meters wide, traveling at tens of kilometers per second, can release the energy of a nuclear explosion upon impact. And smaller objects are harder to detect, especially if they approach from the sun's direction, where our telescopes can't see. The 2013 Chelyabinsk meteor proved that all too clearly. A previously undetected asteroid, about 20 meters in diameter, exploded over Russia with the force of roughly 500 kilotons of TNT. Windows shattered across 6 cities. Over 1,500 people were injured, mostly by glass and debris. It was a wake-up call. But how prepared are we? In recent years, planetary defense has shifted from theoretical to actionable. In 2022, NASA's DART mission, the Double Asteroid Redirection Test, successfully altered the orbit of a small asteroid moonlet, Dimorphos, by crashing into it at high speed. It was the first real test of kinetic impactor technology, a proof that we could, in principle, change the course of a future threat. And it worked better than expected. Dimorphos's orbit shifted by over 30 minutes. The message was clear: we are not helpless. But DART was only a first step. Future systems may include gravity tractors, spacecraft that gently tug an asteroid's orbit using mutual attraction over time, or even laser ablation, heating one side of an asteroid to cause controlled thrust via vaporized rock. These are engineering challenges, but no longer science fiction. Still, there are risks we can't predict. A long-period comet from the Oort cloud could appear with only months of warning. A fragmenting asteroid might produce multiple impactors. And there's always the chance we miss something. A dark rock, fast-moving, on an unexpected trajectory. So what would happen if we were hit truly catastrophically? It depends on the size. A 10-meter rock might explode in the air, startling but harmless. A 100-meter impact could destroy a region. A 1-kilometer asteroid would be globally devastating, darkening skies, lowering temperatures, and collapsing ecosystems. A 10-kilometer object, like the one that killed the dinosaurs, could end civilization. We're not trying to scare ourselves with these scenarios. We're trying to understand them. Because impact events are rare, but they happen. They're part of the planet's history, part of its future. They helped shape the moon, carve basins on Mars, and rewrote biology on Earth. And they will come again. But there's also beauty in this reality. Because for the first time in planetary history, one species is aware. We can see the danger. We can calculate its path. We can prepare. The dinosaurs never had that chance. We do. And in a twist of cosmic irony, the same rocks that once brought life and once ended it may now help us unite as a species, across borders, across disciplines, to defend the only home we know. So when we look at the sky, we're not just stargazing. We're watching for messengers, and if needed, we'll be ready to answer. For every crater gouged into a planetary surface, for every shattered moon or disrupted orbit, there's a deeper truth the cosmos whispers through its ruins. Destruction is never the end. In space, a collision is not simply an erasure. It's a rearrangement of matter, of energy, of potential. When galaxies collide, as the Milky Way and Andromeda eventually will, stars don't often smash into each other. They weave. Their orbits distort. Their clouds of gas compress. And in that chaos, new stars are born. Stellar nurseries ignite where gravity squeezes raw material into the cradle of fusion. What looks like violence from afar is often a genesis up close. Even black holes, formed from the collapse of massive stars, sometimes collide. When they do, they ripple the fabric of space-time itself. Gravitational waves spreading outward at the speed of light, like the echo of thunder after a cosmic lightning strike. We've only just begun to hear them, thanks to instruments like LIGO and Virgo, but their messages are clear. The universe is full of collisions and full of renewal. In planetary systems, the same pattern holds. The Earth's moon was likely born from a cataclysmic impact. Two planetary bodies, Earth and a Mars-sized object we call Theia, slammed together in a young solar system. The resulting debris coalesced into the moon, which stabilized Earth's tilt, influenced tides, and helped make complex life possible. One violent event created billions of years of opportunity. Saturn's rings may have formed from a torn-apart moon, shattered by tidal forces. In their place now orbits a system of unparalleled beauty, a dance of ice and light. Even asteroid belts, regions of wreckage and failed formation, become laboratories of chemistry, holding clues to the earliest days of our system, and occasionally seeding planets with materials that shape biology. This theme extends to us. Our planet's story is not a peaceful one. It's a history of fire and flood, of collisions and convulsions. Yet, From that turbulent origin emerged a world of forests, oceans, cities, and sentience. Had Earth been too quiet, too untouched, we might never have arrived. We are, in a very real sense, children of impact, and we are now observers of impact as well. We watch galaxies tear each other apart through telescopes. We send probes to cratered moons and fractured comets. We simulate the trajectories of rogue asteroids, imagining not just how they would destroy, but how we might divert or survive. This dual awareness of both danger and creativity is a gift, because it allows us to see beyond fear. We don't just ask, what might kill us? We also ask, what has built us? And in doing so, we learn to see the universe not as a place of isolated disasters, but as a system of cycles. Out of collapse comes formation. Out of wreckage, renewal. Even life itself follows this rule. Extinctions, though terrible, open ecological space. After the asteroid that ended the dinosaurs, mammals surged, and eventually humans emerged. A single space rock changed the entire trajectory of Earth's biosphere, not just ending an era, but beginning a new one. The same may be true elsewhere. On distant exoplanets, collisions may have sparked chemistry, formed moons, stirred atmospheres. Perhaps somewhere across the stars, another species is asking the same questions, looking at its sky, its craters, its scars, and wondering where it all began. And maybe, someday, our own descendants will engineer collisions, guiding asteroids to terraform moons, or sending icy comets to seed new oceans on barren worlds. What today feels like threat may tomorrow become tool. The universe does not waste its materials. It recycles. In the end, this is perhaps the most important lesson of all. The universe breaks things apart so it can build something new,